Good morning. Hope you're all having a good day today. Hello, let's see, we've got one person on Zoom and we've got a couple people on YouTube. Good to see you all today. Sorry, my voice is a little gravelly today. Hopefully it won't be too bad. Well, today we're going to wrap up our discussion of RSA and modern cryptography. Show you a little bit more about what goes on behind the scenes of doing a web transaction, and also talk a little bit about how do we know that RSA is really as secure as people say that it is? Like, how do we know that it works? And how do we know that it isn't just like something where you can just easily figure out someone's private keys? Now, you can take, I guess, a little bit of confidence that scientists and mathematicians have been working on trying to crack RSA for years, and they haven't succeeded yet, or at least not in a way that makes it easy to crack the keys. So there is that, but how do we really know that RSA works? So we'll go over that a little bit too. And then finally, we'll wrap up with a walkthrough of this week's assignment. And this week's assignment is going to be interesting. Not only will you write a program that does RSA and can encrypt and decrypt, but you'll also be able to share those encrypted messages with other people in the class, and they'll be able to decrypt yours. And so you'll be actually swapping messages back and forth. So that'll be really cool to do. And this will be one of the last Python assignments. There'll be another one next week. And then I think there's one more later on in the semester, but this is pretty much it. Next week, we're going to be talking about hashing and storing passwords and how those things get cracked by professionals as well. And that'll sort of end the whole topic of encryption, security, and things like that. And then we're moving on to a completely different set of topics for the remainder of the semester. Next week also, I will have kind of a mid-semester check-in with you. I'll have a survey for you to fill out, and just kind of a way for you to see how you're doing in the course, and also give me some feedback about how things are going, just to kind of keep you on track and make sure that you're keeping up with the work. Even though there's any official due dates, it is easy to kind of slip behind, and just want to make sure that you stay caught up so you're not caught doing all the work at the end of the semester. I had that happen last semester with quite a few students who kind of crammed in all the work in the last couple of weeks, and it was just a lot of work for both me and you, right? Not only did you have to do a lot of work, but also I had to do a lot of recording all of those scores and trying to give feedback, and it's just a lot of other stuff is going on as well, so try to keep up with the work. So let's begin. So if you remember from last time, if two parties, let's call them Alice and Bob, want to communicate, they both independently generate their own sets of keys. And we're going to call them APUB for Alice's public key, and APRIV for her private key, and BPUB and BPRIV for Bob's public and private keys. And they did all those calculations that we showed you last time in order to generate the numbers that represent those keys. And then we quickly went over how do Alice and Bob actually communicate. So Alice wants to send Bob a message so that only Bob can read it. And this is actually the same one that we did last time. So Alice wants to take some plain text. She's going to take that plain text and run it through the RSA algorithm, raise it to a power, and do mod n at the end. But what key does she use? What numbers from which key does she plug into that equation? So remember, Alice wants to communicate with Bob. She wants to make sure the message that she sends to Bob, only Bob can read that message. So which key does she use? Now, these are the four keys that she could possibly use. And actually, she does not have this one. She doesn't have Bob's private key because Bob kept that one secret to himself. So she really only has access to these three. Good. So she uses Bob's public key and derives a ciphertext from that. And then Bob takes that ciphertext and runs it through which key in order to decrypt it and get the plaintext back?
His private key.
Good, his private key. Because these go as a pair. So if you're going to encrypt with one, you've got to decrypt with the other. Oh, just a moment here. Forgot to bring up my notes. I had another example for us to do. This is it. Yeah. Okay, let's just go the other direction. So Bob wants to send a message to Alice and ensure that only Alice can read it. Bob is going to take some plain text and run it through which key?
Alice's public key.
Mm-hmm. And then Alice will take that ciphertext and use which key to derive the plaintext back again? Yep, she'll use her private key. So what you can see here is that whenever any party wants to send a message to a second party, they use that second party's keys in order to encrypt and decrypt. So they don't use their own, they use the other ones. Okay, and then I showed you an example of that last time, of encrypting with a public key and then decrypting with a private key. The other thing to remember here is that it doesn't matter which key you use. First, you really could actually use the private key to encrypt and then the public key to decrypt. Now, there is actually a useful use for that. We'll go over that today. But basically, if you encrypt with a private key, then you're going to decrypt with a public key, but everyone has access to the public key, which means anyone can decrypt the message. But what the usefulness for that is to ensure that the message that is being sent came from the person who is sending it, because that's the only person who could have encrypted it. So again, we'll go over that scenario here in a few minutes. But the question here is, how secure is RSA? What prevents Eve from decrypting the ciphertext? Remember, Eve has been listening in on all these transactions going back and forth. Whenever two parties communicate using any kind of encryption, in order to make it as secure as possible, they should always assume that a third party is listening in. And the whole point of this encryption is to give that third party as little information or no information at all about what's being said so that they can't decrypt it. So let's go over a scenario in which Eve is going to try to decrypt the message. First thing we need to establish is, what does Eve have access to? What has Eve been listening to? Remember that she's been listening in on these conversations ever since Alice and Bob started communicating with each other. So she has access to Alice's public key, because remember they exchanged it when they began communicating. She has access to Bob's public key. She does not have access to their private keys. They've kept those secret and they haven't communicated them. And she also has some ciphertext to work with. The public keys, if you recall, are made up of two parts. Public key is made of Alice's encryption exponent and her modulus. And Bob's public key is made up of his encryption exponent and his modulus. So she essentially has, Eve has, these 5 numbers at her disposal. So with these 5 numbers, can she derive the private keys of Alice and Bob? And you might be thinking, well, she has the modulus, right? Modulus was one of those numbers that we calculated. So to decrypt, what she really needs is D, that decryption exponent. And which D does she need? Does she need Alice's D or does she need Bob's D? Remember, well, in this case, Alice has sent a message to Bob, right? And Eve is trying to decrypt that ciphertext that Alice sent to Bob. So she has these 5 numbers. In order to be able to decrypt, she needs one of those D numbers, the D exponents. Which one does she need? Does she need Alice's D or does she need Bob's D?
Bob's D.
Right, she needs Bob's D because the message was encrypted with Bob's public key. So she needs Bob's private exponent. So she needs to calculate that. She needs to calculate that D exponent. So to calculate that exponent, she needs Bob's E exponent. And what was the other number that she needed to be able to calculate D? So she has this one. She has access to that one. But what other number did she need to be able to calculate that D exponent? Well, maybe you don't remember all those calculations we did last time. To find D, that was calculated to be the multiplicative inverse of E mod the totient of N. So if you remember, that was E times D mod the totient of N is equal to 1. So she's got this number, and she has this number, but she needs to calculate the totient of that number. Well, that should be easy, right? She knows that N is composed of 2 numbers. It's the product of 2 numbers because that's just the way the RSA algorithm works. So to calculate the totient of N, she needs those 2 prime numbers that were used to make N the product. So here's where the security of RSA comes in. Factoring a large number, remember n is going to be a huge number, maybe 200, 300 digits long. Factoring a number that big into its prime factors is, as far as we know, a difficult problem. And by difficult, mathematicians and computer scientists mean it takes a long time. It's not impossible, but the word difficult in a computer science and a mathematical sense just means it takes a long time to do. For relatively large numbers like a 4096-bit value of n, it could take years and years, not even years, like, like an age of the universe type time to crack those things. Now, these days, there are actually tools out there that can factor these large numbers. 80 digits, 100 digits, 200 digits, fairly quickly. And by fairly quickly means maybe just a few hours. You can actually bring a whole bunch of computers together. They can all work on the problem. And part of the reason why it can be cracked, in just a matter of hours or even days, is that it's known that that number is composed of two largish prime factors that are all both approximately in the same ballpark with each other. So if you've got a 100-digit product, you know that both those prime numbers are going to be about 50 digits. And so that kind of limits your the range in which you have to look. And also, mathematicians and computer scientists have been working very hard on this problem and have some techniques to find these prime factors somewhat quickly by using statistics and probabilistic techniques where they just kind of guess randomly, but using educated guesses about what the number could be. And then they kind of winnow in on where the actual answer is. I have the assignment this week where you're going to be doing RSA using relatively small numbers. Like we're going to use numbers that are less than 1,000 for the prime numbers. But I have a deep dive assignment where you're going to go in there and actually crack RSA using much bigger numbers. You're going to actually run these algorithms to crack numbers that have 20, 30, 40, 50 digits in them, and see that that can actually be done fairly quickly using one of these algorithms. And so you're going to walk through the entire process of you've got some ciphertext, and you've got an exponent and a modulus, and you need to derive the other exponent. And you're going to use these tools to decrypt it. And by the end of that deep dive, you will actually have decrypted some fairly long ciphertexts into their original text. And it's really kind of cool. Now, this is all using Python, which, as a programming languages go, is kind of slow-ish because it's interpreted. But the tools that professional decryptors and cryptographers use are very, very fast. You can distribute the work amongst many machines, and you can actually, crack these things in a matter of days or weeks. I guess the whole point is, if it's going to take weeks or months to crack something, maybe the message has been expired and it's old information by the time you're able to crack it. And the other way that you can solve this problem is just throw more bits at it, right? So if it's going to take, let's say it'll take a day to crack a key of 1,000 bits. Put on your thinking caps. How long will it take or how many bits do you need to make a key that would take 2 days to crack? So if it takes 1 day to crack a key of 1,000 bits, how long will it take to crack, how many bits will you need to make a key that requires 2 days? You figure that out? Just give me a ballpark answer. No, it's not 2,000. It's not 10,000. Oh, Nunyo on YouTube's got it. It's 1,001 bits. Okay, so if a key has 1,000 bits and it takes a day to crack it, if you add 1 bit to that, you double the number of possibilities. Remember, adding that 1 bit multiplies by 2 the number of combinations, and so therefore it'll take twice as long. So if you make the key twice as long, if you go from 1,000 bits to 2,000 bits, you just made it 2 to the 1,000th time more difficult to crack this key. And that's like multiple ages of the universe. But the mathematicians and computer scientists are working on this problem, and they've been able to leapfrog fairly quickly through these key sizes. We've gone from keys 10, 20 years ago that were 512 bits, 1024 bits, and now the recommended minimum is 4,096 bits to keep this thing from being cracked in a reasonable amount of time. And even 8,192 bits is not unreasonable to use these days. So even though we are doubling the number of bits every couple of years to use as keys, the computers are getting faster and the algorithms to crack them are getting better. Now, someone here mentioned, what about quantum computers? So there is an algorithm in quantum computing called Shor's algorithm. And Shor's algorithm can be used to factor numbers much quicker. It's not instantaneous. Quantum computers are not a miraculous device that can instantaneously factor a number, but it can do it faster. We've seen how if you add 1 bit, it basically doubles the amount of time it takes to factor it. If you add 2 bits, it quadruples the amount of time. So it's a kind of an exponential curve. What a quantum computer will do is flatten that more into a linear one. So as you add 1 bit of information, it only takes a little bit more time to brute force it rather than doubling the time. The problem we have right now is that quantum computers aren't advanced enough. So far, we just can't simply hold a key in it that has 1,024 bits or 2,048 bits because we just don't have quantum computers with that much memory in them. Having a single quantum bit is difficult enough. These days, most quantum computers have no more than maybe about 50 to 100 quantum bits in them. And so to be able to hold a key that has 4,096 bits is just, at this point, out of the realm of possibility. But I don't think it'll be long before quantum computers have that kind of storage at their disposal. What will that mean for us? It means that when quantum computers finally become more affordable for everyday use, then we will hopefully have algorithms in place to encrypt data in ways that even quantum computers can't crack quickly. And that, I think, is going, and because quantum computers can do them faster, and because I think these things are just over the hill, like we're looking at maybe the next 10 to 20 years before quantum computers are available enough and cheap enough that ordinary people can use them, we better have these algorithms kind of in place, ready to go, because as soon as that happens, all this stuff like RSA and ECC is just going to fall by the wayside, right? So it's going to be like this hill that we cross. As soon as we crest that hill, everything needs to be in place to replace all the things we currently use. So maybe that's where you come in. That, you're at a point in your education where you probably ought to start learning about quantum computing. when you transfer to a four-year university, take a course in quantum computing, a course or two, or go find one of the online ones that are available out on the internet and learn a little bit about it so that you can just be ready to march up that hill towards quantum computing when it becomes available. I think if everything goes well in this course, there'll be some time at the very end of the semester where we've got a couple of days with nothing scheduled, and we'll be able to talk a little bit about quantum computing and some of the algorithms that are used in it. So it'll be like a brief one hour, 2 hour introduction to quantum computing. And it's all based on information that I picked up taking one of these online courses that are available on the internet. So I know, just this much about quantum computing, but enough to be able to talk somewhat authoritatively about them. Any questions so far? So the next question is, remember at the beginning of their communication exchange, Alice and Bob have to swap public keys. And Eve is sitting there in the middle listening in. But Alice and Bob also need to assume that not only is Eve listening in, she could potentially also be switching out information. Like maybe she can intercept Alice's public key and replace it with a different one. Or do the same thing with Bob. Bob sends over his public key. Alice could intercept that communication and then switch out that public key for a different one. And Alice might not know that she's not receiving Bob's public key. So how can Alice and Bob be sure that they are receiving the keys that they're supposed to be receiving? So I think about it this way. If I could use well, it's a bit of a stretch, but it's kind of a real-world analogy. Like, let's say you walk into a store and you want to buy something, and the clerk there says, well, I need to see your ID in order to buy this. So you go, fine, I'll show you my driver's license. So you hold up your driver's license. What's on that driver's license that helps the person you're showing it to know that that is, in fact, your driver's license? What's on
a picture of your face.
All right, it's got a picture of your face. What else does your driver's license contain that might help that person, like, confirm your identity?
Like ID numbers and like specific like color codes and stuff.
Yeah, so there might be like security features on the driver's license, or the fact that maybe when you were buying this thing, maybe you filled out a form that you had to put your name and address on it, and now they're going to check to make sure that the name and address that you filled out matches what's on the ID card, right? Just a kind of quick little double check. There could be a description about you, their hair color, eye color, height, weight, all that, things like that. So there's a lot of information on that driver's license that helps that person confirm your identity. But here's where the analogy gets a little strange. How does that person who's looking at your ID card know that that's your ID card and not a fake? How do they know that you're actually showing your ID card and not a fake one that you found on the internet somewhere? All right, so Suri says, well, you look at the security measures on it. Okay, but all that stuff could be faked, right? You could basically just find someone else's ID card and just swap the picture, right?
They can maybe like look you up in the system, like if you're at like the DMV or something.
Oh, okay. So good. So you could go to the entity that issued that ID card. In this case, like the Department of Motor Vehicles. You could go to them, and you could bring that ID card. You could say, "Is this your ID card? Did you issue this ID card?" And then they could look at it, and they could maybe look it up in their system, and they could, maybe they have some other ways of confirming the identity of that ID card, and they can go, "Yes, this is our ID card." And so that would raise your confidence level that you have a valid ID card here. Okay, now here's where things get really strange. How do you know that you actually contacted the DMV and that you didn't walk into a building or a website or you talk to someone on the phone that is faking the whole thing? Maybe they're in cahoots with the ID card holder. How do you know that the DMV is the real one and not a fake? And that's where he goes, there's no reality. Everything is just, but how do you know?
I guess if you really wanted proof, you could ask like some sort of government entity.
No, there we go. So you go to like the next step up, right? Maybe you go to, the governor's office, right? And you go, is that DMV building over there that I walked into, is that the real one? I talked to so-and-so over there. Are they actually employed by the DMV?
How do you know the governor's real
Oh,
though?
yes, right. So you see how this like goes to some weird logical conclusion, right? You can never be sure that the entity that is vouching for another entity is itself not a fake, right? So at some point, this whole like chain has to stop somewhere. Like maybe you talk to the president and you go, is that governor's office the real one? And is that DMV is the real one? And is that ID card the real one? Right? So at some point you have to stop this and go, I implicitly trust that entity at the end of the chain. And once you reach that point, then every other step along the way that works your way back towards that ID card is also implicitly trusted. Does that make sense? Okay, so in the real world, this doesn't really happen, right? It's an absurd analogy. But on the internet, because everything happens just in a fraction of a second, all this stuff is really important. If at any point in that chain that trust is broken, then you can't trust anything else, on this side of that trust. And like I said, it all happens in just a fraction of a second. Any single one of those entities could present to you basically a fake ID and say, I'm pretending to be this identity, but I'm actually not. So when Alice and Bob exchange their public keys, they want to do it in a way that both parties can be sure that they're actually receiving the public keys from the other person. In other words, Alice and Bob need to show their ID cards. They can't just write down their public key on a piece of paper and hand it to the other person. They've got to maybe send it along with their ID card. And so that's what a digital certificate is on the internet. It's basically an ID card. So a digital certificate is a document that contains some information about the person who holds, or the entity that holds the digital certificate. It's got like their name, it's got their address, probably got their email address, and then it has their public key on it. So that's your ID card. It contains a lot of the same information that your regular ID card has.
Does it actually have all that information on it? The name and address and email?
A certificate? Yeah. Yeah. So when you want to go and obtain one of these digital certificates, you usually have to fill out a web form. You have to tell them who you are, your address, email address, maybe, like if you own a domain, a web domain, it might ask for that as well. So any information about you, the ID card holder, and then also it has a little box that says fill in your public key here. So you've generated one of your public keys and you just paste it in.
What happens if you like buy like domain security where it hides all your information?
Well, So when you go obtain a digital certificate, you need to go to a company that is going to essentially vouch for you. It says, so you
Oh yeah,
present,
you're actually right. I've used Let's Encrypt, and you just put in your
uh-huh,
email.
yeah. So a lot of these companies, it kind of depends on how much you pay them. If you pay them not very much money, then they'll just sort of like trust the information you give to them. If you pay a lot of money, let's say $100 a year, $200 a year, then they're going to run a background check. They're going to check, they're going to do a very thorough check to make sure that you are who you say you are before they put their stamp of approval on it. So an organization like Let's Encrypt, it's totally free. They don't check at all, right? You go to like what are some names like Secure Cert or something like that, then you might pay $100 a year, and they might say you need to send in a copy of your ID card, you need to send in maybe 2 forms of identification, and they're going to run a background check, and and make sure you are who you say you are. So when you do that, what's called the certificate authority, the company that you get the certificate from, is going to put their stamp of approval on the bottom of the certificate. It's basically their signature. They're going to sign this document to say, this is this is who you say you are. So a certificate of authority, which is also just abbreviated CA, puts their signature. And their signature is not just simply a scribble. It contains things like their name, their address, and probably their web address, so that anyone who obtains this certificate could go to that address and essentially confirm the identity of the certificate authority. So, right, this is following that chain down there, right? Right. How do I know this ID card was actually issued by the issuer who claims that they are who they are? So you could go to that address and basically confirm the identity of this signature. Well, how do you know that that signature is valid? So you'll follow this address, and what you get there is another certificate. So this would be the CA's digital certificate, and it contains their name, their address, their email address, and their public key, along with a signature. So this certificate authority got their certificate from another certificate authority. You see how this chain is going down? So it contains a signature, a name, address, and the web address of the certificate where that came from. And then that one, contains another one that points to another one. So this can just keep going on and on and on. And eventually, you reach something called a root certificate. So a root certificate is the end of this chain. A root certificate is signed by itself. So the root certificate comes from a certificate authority that has vouched for itself, essentially. and you just implicitly trust them. Now, you may go like, I've never heard of them. I don't know who they are. But you do. You implicitly trust them. When, in most web browsers or built into the operating system itself is a list of root certificates that your computer implicitly trusts. So on my computer here, I've got this application called Keychain Access. And right here is an item that says System Roots. And these are all the root certificates that my computer just implicitly trusts. And it looks like there's several hundred of them. Where did these come from? I didn't put them on there. So the operating system vendor or the website or the web browser vendor put those on there for you. These companies, many of whom I don't actually recognize, paid money to Apple or to Google or whoever made your operating system or made your browser to have their root certificate included in this list. So you just implicitly trust them. Now, if you are totally paranoid and you don't trust any of these certificates that are on here, you could just go through and just highlight them all and delete them. And what that would mean, of course, is that now this chain is completely broken and you won't trust anyone. But then what you could do is you could go to the websites of some of these root certificate owners and you could download them yourself and put them in one by one yourself and actually verify all of them manually. If you are totally paranoid, you could do that. I don't have that kind of time in my life, so I don't do that. But I've heard of people that do. So that's what this kind of chain of trust, that's how that works, is that anytime you've got a digital certificate, you can look at the signature on it and you can follow that to the certificate where that came from. And you can follow that to the certificate where that came from. Let's go ahead and try it. I'm not sure if it's going to work, but let's take a look at the certificate here for this website. This one here was issued by a company called R3, which is really the kind of the parent company for Let's Encrypt. So I can look here at trust. Details. And it says, so this was issued by Let's Encrypt. Got a serial number, signature algorithm. Here's RSA right here. Got the public key for RSA. Here's that exponent. If you remember last time, I talked about a default public exponent. Instead of picking one of the E numbers, you can just use 65,537 because it's prime and it's close to a power of 2. And computer people like that. Computer people like that number because it's easy to remember. 4096-bit key size. And here's a signature right here. And then here, you can go to this web URL and you can, follow that and find their certificate. And then follow that and find their certificate, right? So you can just follow this chain all the way up to finally the root certificate. Eventually you'll get to a root certificate and then that's where the chain stops. Okay, so how do we know then that the certificates that we obtain haven't been changed or altered in some way? For example, if I go to a certificate authority and I give them the certificate information and they put their signature at the bottom of it, what's stopping me from just changing the name here, changing the address so that it's someone else's? In other words, what's preventing me from faking that information? So that's what we're going to learn about next week.
Do they use some sort of hash?
Yeah. We'll learn about checksums and hashing next week. And those can be used to ensure that the contents of the certificate haven't been altered. They're a mathematical calculation based upon the contents of the certificate. Just to kind of give you a preview, and this is not how it's actually done, but one thing you could think about is maybe you could take the ASCII values of every single character in the certificate, and you could just sum those all up. And now you've got a number that's based upon the contents of that certificate. And you put that at the bottom. And then if the contents of the certificate are then altered, then the sum's not going to match up anymore. So someone could take the sum, compare it to the contents of the certificate, sum them up again, and if the numbers don't match, they know the contents have been altered. That's a very, very quick way of doing it, and it's not very secure, but that is an idea that you could use. So you can look at those checksums at the bottom of every certificate and ensure that the contents haven't been altered. Okay? Any questions about that? A question on YouTube is, so to simplify this, do web browsers typically include a list of trusted sources? Yes. Well, it depends. Like Chrome, I think, just uses the built-in operating system's list of root certificates. Firefox is unique in that I believe it has its own list that's separate from the operating system. And there was actually a problem, I don't know how long ago what this was, maybe 10 years ago or so, give or take, where a malware company had actually paid the money to get their root certificate included in the Firefox list of root certificates. And therefore, they were listed as a trusted root certificate. And what that meant was that anytime you went to a malware site that had that other certificate authority vouch for them, you got that nice little lock icon in the corner. So Firefox had to very quickly issue a retraction, basically issue an update to the browser that took out that root certificate and invalidated any copy that was out there. But you can imagine that, the kind of chaos that caused when it was discovered that that malware root certificate was in there. And, it kind of points to the problem is there's this single point of failure, which is you just implicitly trust that list, right? No reasonable person is going to go through that list and verify every single one of them. So there's parts to the web where it's kind of miraculous that it all works because it's based upon, at some point, just somewhere down this chain of information, you just have to trust that everything is working as it's supposed to work. And then we got here, last year, Let's Encrypt root certificate expired and lots of websites that use it couldn't be accessed. That happens too every once in a while. And it occasionally happens on our own websites because I use Let's Encrypt on things like our Jupyter website and our Theo website for the other course. It's up to me, I run those websites, up to me to actually manually renew those certificates. And the Let's Encrypt ones, which are free, only last for 3 months. So every 3 months, I got to go in there and renew that. And occasionally, I forget to do that. And you come to the website, and there's this little warning up here in the lock that says, "Warning: this site is not secure because the certificate expired." It has to be based on trust at some point, right? Or else the whole internet would slow down to a crawl. That's right. Yeah, so at some point there just has to be some trust. Not that it will slow down, it's just that chain of trust then breaks. And so it won't necessarily make it go slower. Well, I mean, it might make it go slower in that everyone now gets these little pop-ups that say the certificate's not valid anymore, and you have to click OK or click I'm going to go trust it anyway, and that, I guess, slows things down. But it's not like the information itself slows down. Yeah, I know you can use cron to do it automatically, but in some cases it doesn't work when you have a custom configuration that the Let's Encrypt is not familiar with, which is the case on our Thea servers. It's a custom configuration. Jupyter actually does it automatically itself, so there's not a problem there. I have other websites that all have custom configurations, and the cron just doesn't work. All right, let's see. Okay, so let's answer the question, how does RSA actually work? We've gone through the calculations, and it seems to work, right? We plug in the numbers, we run it through the formula, and we get ciphertext out, and then we run it through the other formula, and we get the plain text back. But like, how does that actually work? So remember that the ciphertext is equal to the plain text raised to some exponent. And I know there's a modulus involved here, right? But don't worry about that for a moment. Just know that we can take the plain text, we raise it to an exponent, and we get the ciphertext. And then if we then take the ciphertext and then raise that to the d power, we get the plain text back again. Right? So we're going to take the plain text, we're going to raise that to the e power, and then we're going to raise that to the d power. And that should give us our plain text back. So when you take a number and you raise it to an exponent, and then you raise that to an exponent, it can be simplified into just multiplying those exponents together. But we know that E times D is equal to 1 because they're multiplicative inverses of each other. So what we're really doing is P to the 1. So when we take the plain text and we raise it to an exponent, and then we raise that to an exponent, which is just its multiplicative inverse, what we're doing essentially is just canceling those exponents out. And then we get the plain text back. Okay, I know there's some stuff in there where there's that modulus, and when we do the actual encryption, we're using modulus n, but when we calculate E and D, we're doing mod of the totient, which are different numbers. And so, but this is a kind of like the overview that what we're really doing is we're taking two numbers, which when multiplied together are just one, and they cancel out. So what we really need is kind of like a more solid proof that RSA actually works. And let me see if I can do this here. So before we start this, I need to run through a little bit of terminology so you understand what's going on in the calculations. When we say like a number is even, 10 or 24, what makes it even? When you're in grade school, you learn that it just ends with 0, 2, 4, 6, or 8. Right? But that definition of even kind of depends upon us counting in base 10. Right? What if we're counting in base 3? Then we can't say a number is even based upon that last digit because the base is odd, which means it's going to switch back and forth. Which one is the even number? So sort of a mathematical way of saying a number is even is saying that that number is basically a multiple of 2. So you got 2 times some number m, where m is an integer. And then to say a number is odd is to say that it is 1 more than a multiple of 2. Okay, so that gets away from a definition based upon what specific digits are in the number and talks about characteristics of the number. And finally, we can also say that any number, pick any number, and you can represent that number or express that number as some multiple of some other number plus a constant. Right, so we could pick a number like 7, and we could say 7 is 2 times 3 plus 1. Or 7 is 2 times 2 plus 3. Okay, so we can say that any number is some constant more than a multiple of some other number. Okay? So we'll go with like those definitions of some terms. Okay, so let's see if we can do this proof here. So the proof of RSA, first of all, we do the calculation, n is p times q. Remember, those are 2 prime numbers. And we're taking our plain text message, and we're raising it to the e power, and then raising that to the d power. And that should give us our original message back. So we're trying to prove that this is true. We're trying to prove that if I take a message and I raise it to the e power and raise that to the d power, I'll get my original message back. Well, we know that if we raise a power to a power, we can just multiply them. So what we really need to do is show that e times d is equal to 1. And on this previous page over here, I kind of glossed over that, right? I said, you know, they're equal to 1, but they're equal to 1 mod a different number. So what we need to show is that e times d equals 1 mod the totient of n. Okay? So for a number to be equal to 1 mod some other number, it means that that number must be 1 more than a multiple of that modulus number. Okay? So like, let's say we're doing mod 7. 15 is 1 more than 2 times 7, the modulus number. And 22 is 1 more than 3 times 7. And both 15 and 21 are equal to 1 modulus 7. Okay? So we've got all these numbers that are 1 more than a multiple of our modulus number. So that means e times d is equal to 1 more than some multiple of the totient of n, our modulus number, which is right here. And a multiple of the totient means that there's just some integer that we can use to represent that multiple. Okay, so that follows from like this definition here. So we've got some multiple of our number plus a constant. In this case, the constant is 1, and we've got some multiple here. So let's put this E times D back here. Okay, so I took this calculation, this representation for E times D, and I just swapped it back in to that formula that we're trying to prove. And then when you have an exponent that is a sum, you can basically split that exponent up into two parts. So we end up with m to the 1 power times m to the k modulus n, totient of n. And then, of course, this 1 just falls away, right? So now you end up with m times m to the k totient of n. Okay? Good so far? Now, we have Euler's theorem, so this comes back again. Remember, that was a to the totient of n is equal to 1 mod some other number, x. So you got some number, some integer a, and you got some integer x, and as long as those two are co-prime, this formula holds. And in this case, we're working with co-prime numbers, so that's satisfied. Okay, look here. See, this is some number raised to the totient of n, and this is some number raised to the totient of n. So swapping that in times 1 to the k power mod n. Okay, so what did I do there? Here's this m right here. I'm leaving that the same. This can be broken up into m times m to the k power times m to the totient of n power. And so right here, I'm swapping that in for here. Okay? So now I'm left with m times, well, I guess this didn't help out too much here. I'm basically swapping, I'm swapping this in right here. Whoops. This in right here for this, leaving behind that k exponent. Well, anyway, regardless, what we're left with here is m mod n, which is what I was trying to prove. So it's all kind of like thanks to Euler's theorem. Remember I said, what was it, last week, that Euler's theorem was one of those, you know, it looks interesting, but I'm not sure how this is useful. Well, it turns out this is like the whole basis behind RSA working. The fact that this was shown to be true, you know, all those years ago. All this fancy stuff with exponents and modulus, you know, that's all fine and dandy, but it's really the fact that Euler's theorem is true that makes RSA work. Okay, so just as a review of the RSA calculations, we've got choose P and Q, primary numbers. You're going to multiply them together to make a product. You're then going to calculate the totient by multiplying the totient together. calculate some possible E values that are co-prime to that totient, and just pick one of them. And then finally, compute the multiplicative inverse of E and that totient, and then you've got your D number. And so those are the 6 numbers you need. You throw away 3 of them, and you leave behind the E, the D, and the N, and those become the basis of your keys. Any questions about that stuff? So I wanted to show you a video before we stop for a break. Remember I talked about how the 2 parties exchange keys at the beginning. And so these days it's really done using a digital certificate. But I wanted to show you this video, which was called the Diffie-Hellman key exchange. And it shows you in a visual way another way that these keys can be exchanged, again, without using any kind of digital certificate, and hides information from Eve, the eavesdropper. So let me bring that up. And then we'll watch that. It's about 8 minutes long. And then we'll take a little break, and then we'll go into this week's assignment.
After World War II, with most of Europe in ruins, tension grew between the Soviet Union and the United States. It was clear that the next global superpower required the ability to both launch and successfully defend nuclear attacks from intercontinental ballistic missiles. In North America, the most vulnerable point of attack was over the North Pole, so in 1958, a joint effort between United States and Canada was established, known as NORAD, or North American Aerospace Defense Command. An important line of defense was the semi-automatic ground environment. It was an automated system of over 100 long-distance radars scattered across North America. They were connected to computerized radar stations that transmitted tracking data using telephone lines or radio waves. All of this radar information was fed into a primary warning center buried a mile deep inside Cheyenne Mountain in Colorado. This application of machine-to-machine communication allowed operators to make split-second decisions using information transmitted and processed automatically by computers. This idea of being online was quickly adapted and advanced by universities in the following years as they understood the potential of computer networking.
The thing that makes the computer communication network special is that it puts the workers, the team members who are geographically distributed, in touch not only with one another, but with the information base with which they work all the time. And this is obviously going to make a tremendous difference in how we plan, organize, and execute almost everything of any intellectual consequence. If we get into a mode in which everything is handled electronically and your only identification is some little plastic thing you stick into the machinery, then I can imagine that they want to get that settled up with your bank account just right now and put it through all the checks, and that would require a network.
Money transfers were just one of a growing number of applications which required encryption to remain secure. And as the internet grew to encompass millions around the world, a new problem emerged. At the time, encryption required 2 parties to first share a secret random number known as a key. So how could 2 people who have never met agree on a secret shared key without letting Eve, who is always listening, also obtain a copy? In 1976, Whitfield Diffie and Martin Hellman devised an amazing trick to do this. First, let's explore how this trick is done using colors. How could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on 2 facts. 1, it's easy to mix 2 colors together to make a third color. And 2, given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock. Easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they agree publicly on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private colors. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrived at a shared secret color. Notice how Eve is unable to determine this exact color since she needs one of their private colors to do so. And that is the trick. Now, to do this with numbers, we need a numerical procedure, which is easy in one direction and hard in the other. This brings us to modular arithmetic, also known as clock arithmetic. For example, to find 46 mod 12, we could take a rope of length 46 units and wrap it around a clock of 12 units, which is called the modulus, and where the rope ends is the solution. So we say 46 mod 12 is congruent to 10. Easy. Now, to make this work, we use a prime modulus, such as 17, then we find a primitive root of 17, in this case 3, which has this important property that when raised to different exponents, the solution distributes uniformly around the clock. 3 is known as the generator. If we raise 3 to any exponent x, then the solution is equally likely to be any integer between 0 and 17. Now, the reverse procedure is hard. Say, given 12, find the exponent 3 needs to be raised to. This is called the discrete logarithm problem. And now we have our one-way function, easy to perform, but hard to reverse. Given 12, we would have to resort to trial and error to find matching exponents. How hard is this? Well, with small numbers it's easy, but if we use a prime modulus which is hundreds of digits long, it becomes impractical to solve. Even if you had access to all computational power on Earth, it could take thousands of years to run through all possibilities. So the strength of a one-way function is based on the time needed to reverse it. Now, this is our solution. First, Alice and Bob agree publicly on a prime modulus and a generator, in this case 17 and 3. Then, Alice selects a private random number, say 15, and calculates 3 to the power 15 mod 17, and sends this result publicly to Bob. Then Bob selects his private random number, say 13, and calculates 3 to the power 13 mod 17, and sends this result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number to obtain the shared secret, which in this case is 10. Bob takes Alice's public result and raises it to the power of his private number, resulting in the same shared secret. Notice they did the same calculation, though it may not look like it at first. Consider Alice. The 12 she received from Bob was calculated as 3 to the power 13 mod 17. So her calculation was the same as 3 to the power 13 to the power 15 mod 17. Now consider Bob. The 6 he received from Alice was calculated as 3 to the power 15 mod 17. So his calculation was the same as 3 to the power 15 to the power 13. Notice they did the same calculation with the exponents in a different order. When you flip the exponent, the result doesn't change. So they both calculated 3 raised to the power of their private numbers. Without one of these private numbers, 15 or 13, Eve will not be able to find the solution. And this is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers, we can say it's practically impossible for her to break the encryption in a reasonable amount of time. This solves the key exchange problem. It can be used in conjunction with a pseudo-random generator to encrypt messages between people who have never met.
I really like that video because it uses that nifty little color trick to kind of show you what's going on when you raise these exponents, is you're really just kind of mixing those colors together. Well, it's about time to take a break. We'll break for about 10 minutes or so, and then we're going to come back and we will go over and walk through this week's programming assignment. So I'm going to pause the Zoom video, but the YouTube folks, I'll continue to be able to talk to you.
Recording stopped.
Okay. Oh yeah, so you said it's a super explanation. Great video. I love that video. You know, even though it looks like it was made a long time ago, it's still just a fabulous explanation as to kind of what's going on when you do these calculations. Let's see, let me look through some of the chat messages. Oh, the question was, is RSA and OpenSSL the same thing? And they're not the same thing. RSA is an algorithm for doing encryption and decryption. OpenSSL is a set of tools for doing cryptography things on a computer. So it not only does RSA, but it also does things like hashing, which I'll show you next week, digital certificate creation and verification, and it also does encryption algorithms besides RSA. So that's not the only one that can be done. So OpenSSL is kind of like a toolbox with a bunch of tools in it. One of those tools is RSA, but it has many other tools as well. Oh, maybe, why don't we do this? Let me see. Let me see if I can show you something. I've got to find some notes on it first to make sure I do this correctly. So Akash asks, is RSA and Diffie-Hellman both serve the same purpose? Yeah. In today's modern web browsing and web transactions, RSA is used to exchange that secret key that both parties need. Diffie-Hellman was an old way to do it before RSA came along. How they choose which one to use? I think RSA is probably just a little more secure. It's able to use larger numbers, and you know, I'm speculating at this point. I would have to go and do a little research on that before I could answer that with some authority. But why is Diffie-Hellman no longer used? Or what could be is that Diffie-Hellman is just this idea of using these private exponents and not sharing them with the other party. And RSA in that respect is very similar. You've got these private exponents you're not sharing with the other party. But Diffie-Hellman is not only the calculation, it's also this whole protocol. How do these two parties actually communicate these things to each other? Like, how do you indicate this is the number and this is a message and this is my name? How do you actually divide up that message so that both parties understand the parts of the message? I think that's also part of Diffie-Hellman. Okay, let's try this. This is like totally extra stuff here. I'm going to show you using OpenSSL to do RSA. I'm doing this on the command line, but your computer does this behind the scenes. So when your browser needs to exchange certificates or do some encryption or decryption with the other end, it essentially uses these tools, not on the command line, but it uses these tools to do the same thing. So the first thing we need to do is generate a set of keys. So I'm using the OpenSSL command. I'm telling it to generate RSA keys, write the output to this file, and then use this number of bits. And then these dots and pluses are it basically rolling the random dice to generate these prime numbers. A lot of the time it takes to run this algorithm is in choosing those two prime numbers. It doesn't have a list of giant prime numbers to use. There's no way to keep such a list in memory or on disk anywhere. The list would be too huge. So it essentially has to roll the dice, pick a random number, and then see if it's prime. Now the process to check if a number is prime takes some time to do. And so that's what these pluses and dots are. Is it just rolling the dice, check to see if it's prime. If it's not prime, roll the dice again and keep going. If I change the number of bits here, then it takes longer and longer for it to guess and check to see if those numbers are prime. Once it's calculated those numbers, then the rest of the calculations go pretty quickly. I'm going to change this back to 1024 just so it's relatively short. Notice also that in all cases it has picked the same E exponent. It just uses that default 65,537 in all cases. So right now this file that it wrote out is a file that has been kind of compressed and is suitable for exchanging with another computer. And so the contents of it can't be understood by a human because it's all just binary data. So we can actually run a command that'll take that file and split it out into its different fields, and then we can see those fields. So what I told it to do was take those RSA keys, read in the key file, and then spit it out as text so that we can see it. And here we've got, there is a modulus, and it's a giant number. This is just a giant, in this case, base 16 or hexadecimal number. We've got our public exponent, our private exponent. This is the E value here, and this is the D value. This number here is the multiplicative inverse of 65,537 mod this, the totient of this number. Here are the two prime numbers. Again, they're represented in base 16 here, but these are two prime numbers. And then these remaining exponents and coefficients are used for some other calculations that aren't important right now. And then here's the private key, just represented in a base 64 encoding. It's all this information up here, but just base 64 encoded. The other thing we can do is we can take that private key and we can split off just the public part of it. Remember, it's two keys. The private key file actually contains both keys. It contains both the public and the private key. So what we're going to do is we're going to take the private key file and then just peel off the public part of it and write that to its own separate file. Oh, I'm doing the wrong command here. Dash in, key file, dash pub out. Okay, and just like before, this public key is also a compressed file that can't be viewed by humans, so we can look at that as well by loading it in and then viewing it as text. Oops, I did something wrong here. Here we go, pub in, got it. So we can see here, all this public key file contains is the modulus and the exponent, nothing else. No primes, no totient, nothing else, just what someone would need to be able to encrypt data and send it to me. I would give them this, the modulus and the exponent, and they would use that to do the calculations. Okay, so let's go ahead and encrypt something. Now, the thing I have to encrypt has to be shorter than 1024 bits, which I think is 64, 32 characters. Anyway, we'll just do a short little phrase. Let's do something short like, I don't know, we'll just go good morning. And I'm going to put that into a file. Let's call that plain text. Oops, what am I missing here? Oh, wrong quotes. I need to use single quotes for that. There we go. So my plain text file contains just this phrase, good morning. Now I'm going to encrypt that. So I'm going to encrypt it with the public key. I'm using my own keys here, but pretend I have keys from someone else. Pretend these keys that were generated were given to me by someone else. So I'm going to go ahead and encrypt it. Oh, I made a mistake again somewhere in here. Let's see, open SSL, RSA utilities. Here it is. Pub in. So we're inputting a public key. This specifies the name of the key file. We're going to tell it to encrypt. We're going to input our plain text file and output our ciphertext file. Something else is wrong here. I misspelled RSA util. Like one character is out of place and this whole thing doesn't work. There we go. And the ciphertext is just seemingly random gobbledygook characters. We got a few characters in here that are plain text. Some of them have been interpreted as foreign characters, but most of these are just, you know, it's just characters. It's just numbers, basically, stored inside this file. So this is the encrypted data. It's not even like the plain text has been transformed into something else. It's actually been encrypted. And if we look at the length of this file, it is exactly 128 bytes long, which is, oh, that's the number. That's 128 bytes is 1024 bits. So this ciphertext that comes out is exactly equal to the length of the key that we're using. If we had used a key that was 2048 bits, then the file would come out to be 256 bytes, which is the same as 2048 bits. So when you encrypt a single message, what it does is it takes the plain text, it takes all the bytes of the plain text and just crams it all together as one several dozen bit long number. And that one single number gets fed in as the plain text value. So it's not even encrypting one character at a time like we're going to do. It's encrypting the entire message as one giant number. And what comes out is, again, one giant number that is the same length as the modulus. Right? We're doing mod a 1024-bit number at the end of our calculation, which means the number that comes out is itself going to be, at most, 1024 bits. So let's decrypt it. Try to spell everything correctly this time. I'm going to use my private key to decrypt. So tell it, input this file, decrypt. Here's my input ciphertext file. And then what comes out is my plain text. So what really happens behind the scenes is not we're encrypting a plain text like an actual text file, more like we're going to encrypt an AES key that we could use to send to another party. We can use the OpenSSL program again to generate this random key. So although this looks like just random data here, this is just a 16 character random number, essentially. So it's just a bunch of random bytes that have been written to this file. We can do 32 if you want. We can do 32. Now, it's a longer file. So let's go back to 16. You can also use OpenSSL to generate random numbers, but you can see it in base 64 if you want. So a base 64 encoded random number. You could also see it in hex. 32 bytes of random hexadecimal numbers. Okay, so let's go OpenSSL, encrypt, using AES 256. We'll use our password file here. We'll input our plain text. And we'll output our ciphertext. So other than it beginning with this phrase salted, the rest of it is the encrypted data. We took our good morning message and we encrypted it using AES, and now we've got our outputted file. And then we can decrypt it. So we're going to decrypt using the same cipher, AES 256 ECB, our password file, input our ciphertext, and output, we'll call this plaintext 2 so we don't overwrite the original one. And there we go. We got our original one back. So what would happen in reality was we'd actually reverse the order of this whole thing. We would generate a random AES password, write that out to a file, then generate our RSA keys. The other party would be doing the same thing. They would generate their AES password and their keys. We would exchange public keys, so we had each other's public keys, and then we would take those password files and encrypt them using RSA, using the public keys we got from the other party, send that over to the other party, and then they would decrypt them using RSA. And that would now have the two AES passwords that we generated, and then we would use the AES encryption and decryption to actually send and receive messages. So that's a little bit about what goes on behind the scenes when your browser is talking to a web server. Okay, so actually it's been about 15 minutes, so let's come on back and we'll go over this assignment.
Recording in progress.
Okay, I'm going to give you a walkthrough of our RSA assignment, and really there's some calculations to do, but I'm going to walk you through those calculations because I think it's more important for us to get to the really interesting part, which is to exchange messages with each other. We don't have a whole lot of people who are on our Zoom. We've only got 3 people here, so maybe you 3 will be able to do this and follow along. But the rest of you, I need you to catch up as soon as you can, because the rest of your classmates are going to be depending upon you to send and receive these messages to and from each other. So to get started, we're going to download the Lab 6 assignment to our computer. And then we're going to log into our Jupyter website and upload that. We'll open it up and take a look. So we're going to be implementing RSA. We're going to generate a set of public and private keys. We're going to encrypt a string into an array of numbers, and then we're going to decrypt that array of numbers back into the text, the original text. So to get started, we're going to need the random number generator. We're going to need GCD, eGCD, and the multiplicative inverse functions. I provided these for you. So we're going to import the Computer Science 26 library, import our random number generator. Here's the Euclidean algorithm for greatest common divisor. Here's the extended Euclidean algorithm. And then here's the multiplicative inverse. So I'm just going to click in that cell and then press Shift-Enter, and that'll load in the contents of that cell. So to kick off the calculations, we need to select 2 prime numbers. Take a look at this chart. Here's a chart of numbers between 100 and about 1400. Pick 2 prime numbers that you're going to use as the basis for all of your calculations. So just kind of look through here, pick 2 prime numbers, and then in the space below, go ahead and put them in. So I'm going to put 863, and I'll pick 1223 as my 2 prime numbers. Of course, you would keep these secret. You wouldn't tell anyone else what they are. And then once you've done that, go ahead and execute that cell to load that into memory. Next step, compute the modulus. You're just going to multiply P and Q together. So have Python do that for you. And if you want to see what that number is, go ahead and open a new cell, type in N, and you can see what the product is going to be. And then finally compute, no, not finally, but next step is compute the totient. This is easy to do since since N is made up of the product of P and Q, and both P and Q are prime, all we have to do is subtract 1 from each one of them, multiply that together, and we've got our totient. And if you want to see what that number is, go ahead and open a new cell and view the contents of the totient variable. Next, compute a list of possible E values for the encryption. So we need a list of all the possible E values. Now we know what our totient is this big old number here, but if we wanted to write this function so it didn't matter what that totient was, we're going to need a helper function. What we really want to do is we want to say filter. We're going to start with a list of all the numbers between 2 and the totient. So it's going to be something, comma, range 2 in the totient. And we want to find out which of those numbers are coprime to it, and just discard the rest. So we got this huge list of about a million numbers, and we're going to throw away all the ones that aren't coprime. But to know whether a number is coprime, we're going to need to pass it two parameters. The two numbers we want to see if they're coprime. But we can't, right? We can only pass it one parameter. When we use filter, we can only pass it one parameter. So what we're going to do is use that lambda technique. We're going to say define coprime with, and then some number x. And we'll return another function. Actually, let me call this a here. B, return lambda of b, b colon GCD of a comma b is equal to 1. Okay, so we're going to pass in one number a. It's going to plug that number in to this calculation, which will tell us if the GCD of b and a are equal to 1, and then pass back a new function that takes in the b. So down here in my filter section, I'm going to call coprime with and pass in my totient, which I know comes from up here. Okay, so let's press enter there. It's going to think, because this is a huge list it's generating. And if I want to find out how many numbers are in that cell, I can execute this, and there is about 474,000 numbers in that list. So I don't really want to print that all out. It's going to be a huge list. Nevertheless, I do know it contains a whole bunch of numbers in it. And what I need to do is just pick one of them. So I'm going to use my random number generator to do this. I'm going to pick a random number between 0 and the length of this list. And I'll use that as an index into that array. Let's do this as two steps. Let's go index equals rand range between 0 and the length of... Now I call this ES because this is my little play on words here. We're going to pick, well, actually, this is a list of possible E values. So these are my E's. These are the E values, E's. So it's a plural of E. So I'm picking a random number between 0 and the length of my E's. And then I'm going to index into that. So this has just picked a random E value. And I can go ahead and see what the value is by opening up a new cell. I can display it. So this was not the index that it picked. This was the actual E value out of that list. Now here's the thing. Every time I execute that cell up here, it's going to pick a new E value. So once you've picked an E value, don't execute this cell again because you want to remain that to be fixed once you've done that. If you go and you start all over again and you execute the cells from top to bottom, you're going to end up picking a new E value, which is going to change the result of all your calculations from here down below. So next, compute the decryption exponent, D. Remember, D is going to be the multiplicative inverse of E mod the totient. And we have a function to calculate the multiplicative inverse. We pass it E and the totient. And we can open up a cell and find out what it came up with. It came up with this number. And then we can also check to make sure that E times D mod the totient is in fact just 1, and it is. Okay, so we're going to go back and just kind of review things here. We picked 2 prime numbers, P and Q, calculated the product, calculated the totient, found all the possible values of E that are co-prime to the totient, and then picked one of them at random. Then we computed D, the other exponent, by using the multiplicative inverse function, which was defined up at the top of the page, and then checked to make sure that those, when multiplied together, gives us just 1. So now we're ready to assemble our private and public keys. So our public key is just a tuple containing the E value and the N value, and our private key is a tuple containing the D value and the N value. So just execute that cell, and then you can see what the public and private keys are. You can see they're just pairs of numbers, and in both of them, the modulus is the same, and the E and D values are different. So now we're ready to start encrypting things. We're going to encrypt a single value. Here's the formula for doing RSA encryption. So if you're given a key and a value to encrypt, we need to take our value, which is our P, raise it to, now remember the key is one of these things over here. It's a tuple. It's not a single number, it's a pair of numbers. So we need to raise it to the first number in the tuple, and then do a mod, the second number in the tuple. So we're going to take our value, raise it to the key's first value, and then do a mod, the key's second value. And we'll just check to make sure that worked. And it does. So here's our key, 17 and 391. Here's the value that we are encrypting, and when we encrypt it, we get 361. Next, we're going to encrypt a byte string. So this function up here, RSA function, just encrypts a single plain text value. We want to do a whole string. Now remember, normally, if you use RSA to encrypt something, you're not going to encrypt one character at a time, because that means if you encrypt the letter A and you get some number out, and then you encrypt the letter A again, you'll get that same number out again. And by encrypting one single character at a time, the ciphertext is still subject to the same statistical analysis that you could do on the plain text. You could see what the most common letter is, and you could therefore infer that that was either an E or an N or a T or a space or something like that. But that's what we're going to do. We're going to do character by character encryption because it's just easier for us rather than taking a message and cramming it all together as one single number, because that would require our modulus to be much bigger. It would require our prime numbers to be much bigger. And I just want you to realize that this is RSA encryption, but at a smaller scale. The real RSA encryption uses much, much bigger numbers, and we're just not going to do that here. Okay, so we're going to encrypt a byte string using a given key. Now our RSA function takes 2 values. But if we're going to use something like map, we're going to map the RSA function onto the byte string. Well, our RSA function takes 2 parameters, but when we use map, we have to pass it a function that uses only 1. So again, here's where that lambda technique comes into play. Let's define a function called, let's call it RSA factory. We're going to give it one of the values, and we're going to hand back a function that takes the other value. Okay, so our RSA factory takes in a key, which remains constant as we're encrypting a single string, and it returns a function that takes in a v, the value that we're going to encrypt, and then just plugs it into our existing RSA function that takes in a key and a value. So now we can map our RSA factory, pass it the key. It'll return to us a function that accepts a value, and then it'll map that function to every single character or every single value in our byte string. And if I run this assertion, we can see there's no errors. So let's go ahead and try to just run this ourselves and see what happens. So if I go encrypt using my public key, the byte string hello, I get this array out. And notice here that the two L's both encrypted to the same values here. So if we received this, we would know that these were the same two letters. We wouldn't know what the letters were, but we know that they were the same. And we would also know this is a 5-character string. So we might be able to try to guess, what these letters are. Let's do another one. Let's encrypt with our private key. Let's do another word. Well, let's just encrypt RSA. That. Okay, in this case, we get 3 numbers out. This number corresponds to the R, this corresponds to the S, and this corresponds to the A. So notice I can use either key to do the encryption. And the other thing I want you to keep in mind as we go through these is that up here, we said public is equal to these two numbers together. So when I encrypt, I can either put in the name of the key, which is pub or priv, or I could actually put in their values. If I copy the value of my public key, and I'm going to open up a new cell, I'm going to say encrypt, and instead of putting in the word pub, I'm just going to paste in the actual value of the key. I get the same thing. So when you're encrypting and decrypting, you don't have to put a variable name there. You can put the actual tuple values, the actual key itself. And this is going to become important because when we get through all of this, you're going to be posting your public key up on a public place where your classmates can get to it, and they're going to copy and paste your public key into their decryption functions. And so they're not going to use a variable name, they're going to use the actual key itself. All right, so we're going to decrypt an array of numbers. Again, we'll need a lambda function for this. So let's call this define. Now I can't call it RSA factory. Actually, you know what? I could just reuse that same RSA factory I already have, right? Because it's going to do the same thing. It takes in a key, and then it's going to return a function that takes in a value. And whether you encrypt or decrypt, you're using the same RSA algorithm, you're using the same calculation, you're just using a different key. So here I'm just going to say map RSA factory pass it the key, and the other parameter to map is the array that we want to do this RSA function to. And then finally, this gets embedded inside of a call to bytes, which is going to convert that array back to a byte string. And then let's try this out, and no errors, so that worked. So here's what we can do, is we can go decrypt. We'll pass in a key. So remember up here we have an encryption with my public key. So I should be able to decrypt with my private key. And then we're going to pass in an actual string that was encrypted, or an actual array. And thinking, we get back our original plain text. Let's try that again. Let's go decrypt. Now instead of using priv, well actually here, instead of using pub, I can use my actual public key, or I can use the variable name pub. And then I'm going to pass in the encrypted array. And thinking, we get back our plain text. So again, it doesn't matter whether you encrypt or decrypt with your public or your private key, as long as you use the other one to decrypt, it works. Okay, so one thing you probably noticed there was it took a while to kind of grind through those numbers. If you have a longer phrase that you are encrypting or decrypting, it takes longer to do the calculations. Let's try something that's longer here. Let's go encrypt with my private public key. Let's do something that's longer, like a phrase or something like that. Let me think about a phrase that we could use. How about this? May the force be with you. Okay, so there's my encrypted string. Notice it took about 5 or 10 seconds to generate that. And then let me copy this. And then we'll do a decrypt. And here's my list that I'm going to decrypt. And then I just have to insert my private key in front. And then think. Still thinking. You can see this star here means it's still working on this. So what's it doing while it's thinking? Oh, there it goes. And then we got it back. So that took about 15 seconds or so, 15 to 20 seconds for it to work through those numbers. So why is it taking so long? Because we're taking that the plain text value, or the ciphertext value, which is this number, 622,796, and then we're raising it to this power, right, to some 6-digit number. So you got a 6-digit number raised to a 6-digit number power, and then you're doing, finally at the end, you're doing the mod the 7-digit number. So when you raise that big number to the other big number, you get this gigantic number. And then you do a mod at the very end. And you got to do that for every single one of the characters. So it takes a long time to grind through those calculations. So I'm going to show you a way to make that faster. Oh, the question is this all being done on our end? No. When you hit Shift-Enter, your cell gets sent over to the Jupyter server. It's executed on the server end, and the results are sent back to you. Yeah, poor little server. It's been thinking hard about this. Actually, let's do this decryption again. And up here, maybe we can see this number change. No? It's holding pretty steady at about 158 megabytes of memory. And that's possibly the case because once it encrypts one character, it can just throw away the result of that calculation. It can throw away the intermediate results of the calculation and just keep the answer. Okay, but let me show you how to make this faster. There is a built-in exponent function, but it does modular exponents. Modular exponents can be made to be very fast. Because you're doing a mod, what you can do is instead of doing the mod at the very end, you can use the properties of the modular numbers to do a mod as you're doing the calculation. So you can think about exponent as being just repeated multiplication. So if you want to multiply a number by itself a certain number of times, you can go ahead and multiply it by itself and then do a mod to keep the number small again, and then multiply it by itself, and then do a mod again. Multiply by itself, do a mod again. So every time you do that multiplication, you do a mod, and the number stays reasonably small. There's another trick that it uses that has to do with the binary representation of the exponent that can speed it up as well. So if you are doing a modular exponent of a 6-digit number, which is going to be roughly about a 20-digit binary number, you don't have to do the multiplication by itself, 600,000 times. All you have to do it is 20 times the length of the binary number, and it goes super fast. So it does in the log of the exponent number of steps. It does the exponent. So it's very, very fast. And you're going to see this here in just a moment, just how fast this is. So let's go up to our RSA function up here. And instead of saying return the value, raise the exponent, and then the mod, we're going to replace this all with a call to pow, which is the power function. And then we're just going to pass in these 3 values. It's the value, key 0, and then key 1. So this is the base of the exponent, this is the exponent value, and this is the modulus. Okay, now that I redefined that RSA function, I've got to redefine everything that depends on it, which is this one, and this one, and this one. And then these encrypts, which were small to begin with. Let's try this one here. This may the force be with you. You can see just how fast that is, right? That took about 5 or 10 seconds to run before, and here it just took a fraction of a second to do. And then we'll do the decrypt, so I got to redefine this function. And then here, run that assertion. And then this one here, actually, let's do this one. Let's do the big one right here. This one took about 20 seconds to do before. Okay, ready? Done, right? That took less than a second to run through that. So this modular exponent function is super, super fast. And it has nothing to do with that function being like already compiled. It's the fact that the algorithm is fundamentally different to do modular exponent. You're doing modulus as you go. That keeps the numbers relatively small. And also you do a little trick with the binary representation of the exponent, and you can reduce the number of calculations you have to do from being proportional to the size of the exponent to instead being proportional to the logarithm of the exponent. That makes it really, really fast. Okay, so now that all that's all working, we're now ready to start exchanging messages with your classmates. So the first thing you do is post your public key. I have a Google Docs spreadsheet available. And you're going to take your name, you're going to put it here. And then you're going to go find your public exponent, or your public key. So you're going to scroll up here, scroll up, find your public key. Where is it? Here it is. And then you're just going to paste that in. And we'll come back down to the section here. So encrypt a few strings and post them. So you're going to use your private key, and you're going to come up with some strings to encrypt. And you're not going to post that array of numbers. I have a function here called print wrap and one called serialize. That's basically going to take your number, do a take your array, do a base 64 encoding on it, so it'll be a nice compact block of text that you can post rather than this big, huge array of numbers. So let's take my key. I'm going to use my private key. Let's swap in here. May the force be with you. And then we'll do our encrypt. And you see you get this nice block of base 64 encoded text. So you can then take this, go over to our discussion area. And there should be a discussion here called RSA messages. You'll click on reply, paste in that body of text, and click on post reply. And now repeat that process 2 more times for a total of 3 strings that you're going to encrypt. So I want 3 separate replies, not one message with 3 things in it, but 3 separate messages. And then wait a day or so for your classmates to do the same thing. And then I want you to find 2 messages posted by your classmates and decrypt them. So you'll go to the spreadsheet, find their public key, find one of their encrypted messages, and run it through this decrypt function. Paste in their public key, paste in their ciphertext, which you can just copy and paste right off of their posting, and then decrypt it. Take that decrypted string, go back to the discussion area, click on reply to their encrypted string, and then paste in the decrypted string. So you're going to do that for 2 postings by 2 different classmates. So let's run through that again. You are going to encrypt 3 strings and post those along with your public key. And then you are going to decrypt 2 strings using their public key. And then reply to those. Why 3 and 2? Well, it gives people who are running a little behind always something that's available for them to do. All right, so if you post 3 and reply to 2, there's always going to be some postings out there that haven't been replied to yet. And there will always be at least something for someone to go ahead and decrypt, even if they're a little bit late. Which means not necessarily all of yours will get decrypted. So you're going to post the encrypted text, and you're going to post as a reply the decrypted text. Now, in some cases, it's not going to work. In some cases, you do the decrypt, and it just doesn't work. Here are some things to look for. One is make sure you're using the correct key. If you encrypted with your private key, which you should do, then the other person is going to have to decrypt with your public key. So make sure on the Google spreadsheet that you posted your public key and not your private key. If you posted your private key, then you encrypted with your private key, and they're trying to decrypt with your private key, and it's not going to work. Make sure that you chose 2 prime numbers to begin with. If you did not choose 2 prime numbers, if one of them was not a prime number, all the calculations are not going to work. I mean, it may appear that you're able to encrypt, but then when someone goes to decrypt, there's not going to be that nice, one-to-one mapping between the encrypted data and the decrypted data. We saw that a couple weeks ago. If you don't choose 2 numbers that are essentially co-prime with each other, then you get repetitions in the encrypted data, and it's not able to decrypt it correctly. You'll get a message about values not being between 0 and 255. So the decryption is just not working. So if that happens, if it just doesn't work and despite all of your debugging efforts, you're not able to get it to decrypt, go ahead and reply to the message and say, I could not get this to decrypt. And maybe you can speculate on why you think it is. Maybe you think that it's not using the correct key, or the key hasn't been generated correctly. But anyway, just say like, I couldn't get this to decrypt, and hopefully the original author will go back and correct whatever's going on. If that happens, go ahead and find another string to try to decrypt. So the goal is to eventually decrypt 2 strings. If you find that you're just unable to decrypt any string, they all are not working, then it's most likely that something's happening on your end. Maybe something's happening in your functions. Go back and check the way you've written your functions against the way that I showed you on the screen, and just double check to make sure that all the algorithms are correct. Okay, so to recap there, if you try to decrypt someone's string and it doesn't work, go ahead and just say so. If you're unable to decrypt anyone's strings, like you try to do 10 of them and none of them are working, chances are the problem's on your end, not on their end, and you need to go and review all of the formulas and the calculations in your notebook. So if it doesn't work for 1 or 2, it's probably on their end. If it doesn't work for any of them, it's probably on your end. So that's the assignment for this week, is to do this RSA exchange of messages. And yeah, keep it clean, folks, right? Right? Don't go too crazy with the phrases, but you can find like phrases out of movies. You can find poems, or whatever you want, as long as it's like interesting, pithy, funny, whatever, go for it. And I will mark this assignment done once I see those 3 messages, no, not those 3, those 5 messages that you've posted, the 3 messages with the encrypted strings and 2 decrypts. So once you do those 5 things, then I'll mark the assignment complete. And also you need to turn in the Python notebook. So just like before, you're going to go File, Download as, Python notebook, and then upload your Python notebook as the submission for this assignment. Okay. So I know I went through that kind of quickly, but you can rewind the video and you can pause at the appropriate places to find out where you need to fix things or to catch up. And then hopefully you can get all the Python stuff done, and then you'll be able to complete this assignment. Next week, we're going to be going into hashing and password cracking. So I'm going to show you how passwords get stored on a computer system, and then what you can do with that. If you obtain what's called the hash of a password, how can you reverse that and get the original password back? The answer is you can't do it directly. You got to use an indirect method for getting it. It's a function. It's a one-way function that can't be reversed easily. You have to resort to a brute force attack to be able to crack a password. But how can you do that reasonably quickly? So I'll show you that. And that will be Monday and Wednesday of next week. And then once that is done, we are basically finished with the first half of the semester. And then we will go on to a completely different set of topics: combinations and permutations, sets, regular expressions, finite state machines, compilers, parsers. We're kind of using programming languages as the vehicle for explaining and diving into this set of topics. The first half of the semester, we use cryptography as our vehicle. This is where we've ended up. We've ended up with cryptography at the very end. And then we're using compilers and programming languages as the vehicle for the next set of topics. Some of those chapters we're going to go through in like one day. Like for sets, actually, we really only need 1 day to go over the basic operations on sets, like intersection, union, difference, exclusive OR. And then we will use that information to be able to do the subsequent topics on things like graph theory, which can be represented as a set of edges and vertices, and doing the algorithms on that. Okay, so let's see. Am I going to cover methods to improve password security on top of hashing, like salting and peppering? Yeah, I'll briefly mention things like salts and things like that to show you how, as a programmer, you can improve the security of passwords. You, as a user, can't do much about that, but you can do things to improve the kinds of passwords you pick, but you can't do a whole lot about how those passwords get stored on the server. But there are things you can look for to determine if they're using those techniques or not. Great. I think this was a great day. We covered a lot of ground, but we brought kind of all of this to a close, and I'm really excited to see all the phrases that you've encrypted and posted on our discussion boards. Okay, I actually have to go. Actually, I realize I'm falling behind on my schedule, so I gotta go. I'll take off. I will see you all later. I don't have time to chat. I just realized how late it was. And so take it easy, everyone. Have a great day, and goodbye. And same for you, just you YouTube folks. I gotta go right away. And I will talk to you either tomorrow, on Thursday for my C programming class, or on Monday for hashing and passwords in this class. Bye-bye.